Yeah. So good afternoon, one and all. I welcome you all for the third talk as a part of Popular Science Talk Series 1, organized by the Center for Excellence in Mathematical Biology. Today we are privileged to have Dr. Prakash Tripathi, an assistant professor at the Department of Mathematics, Central University of Rajasthan. Before joining Central University of Rajasthan, Dr. Tripathi completed his PhD from IIT Mandi in 2015 in the area of
Darshan sir,
mathematical.
Dr. Darshan, can you move the slide little up? The slide hasn't yet moved.
Sure.
Yeah, okay. Yeah, this is much better. Yes, please go ahead.
Yeah. So Dr. Tripathi is an expert of mathematical ecology, disease modeling, and nonlinear dynamics. He has more than 10 years of teaching experience and as well as research. He has published more than 50 research articles in the various journals like Journal of Mathematical Biology, Chaos, Bulletin of Mathematical Biology, Journal of Franklin Institute, Nonlinear Dynamics, and so on. Dr. Tripathi has also attended and delivered various talks at the international and national conferences and workshops across India and abroad. Apart from this, Dr. Tripathi has also obtained various international travel supports from various funding agencies like SMB USA, Serb India, IIT Mandi, and so on. Besides this, Dr. Tripathi has been awarded 3 research projects, one from the UGC and other from SERB ECRA and as well as SERB matrices. Dr. Tripathi has guided various students at the graduate, postgraduate, and PhD level. Many of his students are pursuing their higher studies abroad. Dr. Tripathi is also life member of various academic bodies like Society of Mathematical Biology USA, Indian Science Congress Association, Indian Mathematical Society, Society of Industrial and Applied Mathematics USA. Today, Dr. Tripathi will be talking to us on the topic of understanding of non-dimensionalization via a bacterial growth model, why, how, and when. Now, with these few words, I welcome Dr. Tripathi to deliver his talk.
Thank you so much, Professor Darshan. So let me share my screen. Go ahead. So let me first thank to the Sri Satya Sai Institute of Higher Learning and more precisely Center for Excellence in Mathematical Biology for giving me this opportunity to talk in this popular science series talk series 1 on the theme of mathematical biology, especially to Professor Bamsi and Professor Darshan, who invited me for this talk. So I hope, sir, my screen will be visible. Let me.
Yes, yeah.
Okay.
Yeah, you could maximize. Yes, this is fine.
Yeah. So as Dr. Darshan already stated that I will be talking about the non-dimensionalization. So non-dimensionalization, as you know, that we generally do while doing modeling of biological system. Especially this kind of technique is very useful when we do the modeling in modeling using differential equations, like in control theory, modeling of biological systems. This kind of technique is very useful. So I thought that we can talk about this. So I have divided my talk into these parts. In the first part, basically, I will talk very simple things, fundamental things related to the unit dimension, because we are going to talk about non-dimensionalization. So little bit we will recall about this and how mathematical modeling comes in picture when we talk about the non-dimensional analysis. Then we will go to the non-dimensionalization. So you see, there are two things. One is the dimensional analysis. That means we want to check whether my equation, whatever you have developed by mathematical modeling of any kind of biological system, whether this is dimensionally correct or not, whether this is homogeneous dimensionally or not. This is one part. But the other part is that when you have many parameters and variables in your system, then you want to rescale the variables. Those are present in the model system, or you want to non-dimensionalize the system because you want to make your system simpler, easier to calculate or to analyze. So there are 2 points that we are going to talk about here. One is the dimensional analysis, the other is the non-dimensionalization. So then we will try to understand what is non-dimensionalization, how we do the non-dimensionalization, and what are the advantages. In the different ways, I will try to make you understand that in different way, actually, it is going to benefit when you non-dimensionalize your system. But also, there are people who are doing the experimental research. They don't like this kind of thing, but mathematicians like much because they want to calculate the different kind of things. So then we will talk about that with what purpose we have to non-dimensionalize our system. I will take then in the last bacterial growth model and we will learn the whole process precisely. So, sir, I think that I am much audible. Everything is going good.
Yes, sir. If there is an issue, we'll get back.
Okay.
Yes.
So let us just recall the very small things. How you define the quantity? Quantity is simply defined a number or amount of something. Or you also define like some kind of physical quantity. That may be the weight may be there, the time may be there. Okay, this kind of things we call quantity. But how you represent this quantity means how much quantity is there to represent that, to express that. We use some kind of standards, right? Those standards are used to express the result or the measurement of the quantity. So these standards actually we define as the unit of the quantity. So like if you talk about without unit or without any reference of unit or measurement, for example, somebody says you that there is a huge stock of wheat in the storage or go down, then this is a vague kind of a statement. But if you say that there is precisely 3,000 kilogram of wheat in the go down, then the idea is very clear. So this 3,000 is the number that is followed by the unit kilogram. So weight is your quantity here, and that is we are using the kilogram unit, then the picture becomes clear. Actually, it is somehow is going to give you a comparison of the measurement that you are going to do. Okay, then the units, how the units are represented. So there are some fundamental quantities like you tell the weight, time, and the length. So those actually to represent these 3 fundamental quantities, there were many systems. CGS system, you are well familiar, MKS system. Then in the last, in 1960, what the people has done in the SI International System of Units, they have modified this MKS system and included 4 more quantities into this. And these are the 7 fundamental quantities and their units are there. Actually, with the help of these, we can represent the unit of any kind of quantity, any physical quantity. So now we'll come to the dimension, how you define the dimension. So suppose you have some physical quantity and you want to express that physical quantity in the terms of the fundamental quantities, 3 fundamental quantities, namely length, mass, and time. So are there any combination of these 3 quantities? So whatever you get as a group of these 3 fundamental quantities to represent a physical quantity, that is called the dimension of that physical quantity. In other language, very easily you can say that it is nothing but just raising the units of the fundamental quantities, power of the units of the fundamental quantities to get the dimension or unit of the physical quantity in which you are interested. Like if you talk about the volume, then volume is nothing but it is the product of the 3 lengths, right? L cross L cross L, so L cube you get. Similarly about the velocity. So, but you don't be associate that dimension and units are dependent, both are dependent. Actually, dimension may be different, unit may be different. Unit you can choose by your own, right? You can take the for the length, you can use the kilometer. For the time, you can R, you can use the second. But the unit for the speed will be LT-1. Okay. So there are also some quantities, those are without any dimension. Like if you talk about angle, so the dimension of angle will be dimension of arc upon dimension of radius. So this is a pure number, and any pure number do not have any dimension. So we will come to all these things when we will take some examples. How you associate the mathematical modeling with this dimension kind of things. So you see, when you go and model any problem or any biological system, then you have the different kind of variables, parameters, and constants involved into that model. Those variables, constant, and parameters must be measured. They must be measured in the terms of different kind of units. Like for the time, if you use the 19 second, then second, yes, stands for second, is a physical quantity, and this 19 is now followed by this second. So it has a proper meaning. If you are not going to use here any unit, then 19 has no meaning. What you are talking about 19? So 19 second has a proper meaning. So to check whether any model or whatever the equation you have developed, they are in that the parameters, variables, and the constants are having proper unit. We start with this. What you do, you just check the dimension of the left hand side is same as the dimension of right hand side or not. So if this is happening, then your model is called dimensionally homogeneous. So you see, we'll take a very simple example. Suppose you are applying force on some body, and body is moving in a straight line, and force is in the movement of the body in that straight line, and it is proportional to the cube of the velocity. Then how you model this problem? F equal to some constant k times v cube. Okay. So let us check whether the dimension of left hand side and right hand side are same or not. So if I take the dimension of left hand side, this is the force, and the dimension of force is mlt minus 2, m for mass, l for distance, and t for time. And the dimension of kv cube is nothing but dimension of k and dimension of lt minus 1 power 3, and then you will get actually mlt minus 2 equal to dimension of k times l3 t minus 3. So if you want to make this equation f equal to kv cube dimensionally homogeneous, then you have to set the dimension of k in such a way so that the left hand side and right hand side are same. Those are dimension of LHS and RHS, right hand side and left hand side. So what you have to do, you have to set this dimension of k as ml minus 2t. Whenever it is multiplied with this, then both side dimension will be same. So you say that my equation is dimensionally consistent once the dimension of the left hand side is same as dimension of right hand side. Many times when you are going, so I think before this slide, you people have got what I have explained. So actually these are very small things that I'm going to talk about in this slide number 8. But they are very important when you are going to check whether your differential equation or any equation that you have modeled, it is dimensionally correct or not. So these things are small, but they are very important. Like suppose you have any term which is the argument of any function which has the Taylor series expansion like cos alpha t, then the argument should be dimension free, right? Argument should be there should be no dimension of argument. Like alpha t, if you say t is time, its dimension is t inverse, so alpha must have dimension of t. Otherwise, it will increase the power and you will be in trouble. Similarly, how you find the dimension of any derivative? So if you want to learn this, then you go to the definition of the derivative. What is the derivative? Derivative is the limiting value of some ratio, right? Like you say the dv over dt. So this is nothing but this is limit delta t tends to 0, del v upon del t. So it is just ratio del v upon del t, but it is the instantaneous ratio. So you have to find out for the dimension of dv over dt, you have to find out the dimension of v upon dimension of t. So this is lt minus 2. Again, sir, I think screen is gone. Yeah.
Gone, huh?
Maybe I think every yeah, you can share again.
No?
Yes,
Yes.
it is okay. So similarly, you can find out the dimension of the partial derivative, second derivative, like is second derivative del 2v del x square. So it will be dimension of v upon dimension of x square. So it will be L minus 1 t minus 1. And if two quantities have same dimension, then only you can add. You think about a mathematical model like predator prey model or any model you write. So how you add these terms in the right hand side? Because these terms have the same dimension, so you are able to add it. But if the terms are not having the same dimension, then you are going to multiply or divide those terms or those quantities. So terms are quantities, okay? So pure numbers are not having any dimension, they are dimensionless. So whenever you will go and call that the particular quantity is dimensionless, then you are going to tell that when you find the dimension of that quantity, then it should be coming a number because number has no dimension. Yes, sir, please go ahead. Next slide. And we will talk about dimensional analysis. Dimensional analysis, before that, let us learn what is dimensional equation. So suppose you have got the dimension of some physical quantity and you represent it into the form of equation in the terms of some other dimensions, then it is called the dimensional equation. Dimensional analysis ensures you that whether the dimension of each term in that model have the same dimension or not. Like you talk about this equation, del P dP over dr minus rho v upon r square. Here P is pressure, rho is density, v is velocity, r is distance. So sir, go to next slide. So let us check whether this is dimensionally correct or not. So for this, I have just here calculated the dimension of each term, dimension of pressure, density, velocity, everything I have calculated because I have to put there. So left hand side, if you will see, this is the derivative dP over dr. So that its dimension will be dimension of P over dimension of R. So dimension of P is pressure. So this is the dimension of P upon L. So this is the right and left hand side dimension. But the right hand side dimension, dimension of rho, dimension of V upon dimension of R square. So it is ML minus 40 minus 1. So you are seeing that the dimension of left hand side is not same as the dimension of right hand side. So whatever the equation you have written, this is not actually dimensionally correct. We have to again go into that and we have to add some term, multiply some term or divide some term and check whether the dimension of both sides are same or not. I will take example, biological example, and I will show you that how you do it. Please, sir, go ahead. So now this was one part that I have already mentioned you in the starting of my talk that we will talk about the dimensional analysis. So for that, I have discussed so many concepts. The word itself says its definition. That means to making the terms, your parameters and variables present in the equation dimension free. That's it. This is the definition. And scaling and non-dimensionalization both are actually used interchangeably. They are same thing. Scaling is a trick that is going to give you the idea how you non-dimensionalize the given differential equation. So non-dimensionalization is partial or full removal of physical dimensions from the equation involving the physical quantities. How you do this? By rescaling. In the scaling, what you do? You introduce the suitable variables. So there are old variables in the model. With the help of scaling, we introduce the new variable with a certain constant, and we develop the new model from there. That is the non-dimensionalized model. So it is a technique, it is a technique to make all the variables and parameters dimension free or unitless. And also it is technique to reduce the number of variables, reduce the number of parameters, because you may have the two-dimensional system or higher dimensional system or complicated system, which may be having the more number of parameters. Then when you are going to find out solution or equilibrium solution in the terms of the parametric conditions, then the parametric conditions may be very complicated. So to avoid these kind of complicacy, what you do, you try to non-dimensionalize system. After the non-dimensionalization, you want to recover the result of the older system or original system. Yes, sir. Please, next slide. So this is the reason actually why we are going to do the non-dimensionalization. And this technique is very useful if you are going to model any physical system that is involving differential equation, like in control theory, modeling of biological system, modeling the non-linear dynamical systems, where this kind of non-dimensionalization becomes very important. Yes, sir. And you can also, as I told you, that you can also recover the properties by the non-dimensionalization. So let me see what is the, let me show you what is the trick. Suppose you have any mathematical variable z. So we introduce the new variable z bar equal to z minus z0 upon zc, z minus z0 upon zc. So here z0 is the some reference value of this z, variable z. So in general, when you are going to use this technique of scaling in any model, then it is taken 0. Okay, so you are just going to do the scaling by the constant term, like z equal to zc into z bar, and suitably you choose this zc so that it is going to reduce the number of parameters, and everything will be converted into the new variable z bar. So this zc, there is no hard fast rule, specific rule to choose the value of zc. This will depend on your goal of the study, what actually you want to obtain from your model analysis. Accordingly, you have to choose the value of zc. So if you want to have the particular parameter in the model, you want to see the, you want to observe or investigate the impact of that parameter, then you have to choose this ZC in such a way so that this parameter should remain in the model. Otherwise, it will create a problem for you. How you will see the investigate the impact of that parameter? Yes, sir. So here we will take a very simple problem. As I told you that this is very useful when you are going to model any biological system. So this is spruce budworm outbreak model. And I'm not going to detail about the model, but let us see how this technique works here. So it is actually, there is a reference number 2 in the Ludwig paper. Actually, this model has been developed. Here, Bt is the density of the budworm at any time t, R is the intrinsic growth rate. Every meaning of every term is as it is, as we are generally talking in the model. Beta is the predation rate, alpha is half saturation constant. And this B0 is the initial density of B at the time t equal to 0. So this is the predation term, and it was chosen by Ludwig et al. It is given there. You for the detail, you can read this paper. Sir, next slide. So here, what actually we are going to make you learn step by step how you go and non-dimensionalize your system. So you see, step number 1, what you do, you just identify all the parameters, variables, and other things present in the system, and just find the dimension of those quantities and put into the table. So here you see t is time, so its dimension is t. B is the density of the budworm. So density means what? Density means mass upon volume. So volume का dimension क्या हो? L3. So m upon L3. So it will be m L minus 3. Okay. R is the intrinsic growth rate per unit time, T inverse. So K is the carrying capacity. This is again density, ml minus 3. Alpha is saturation factor. So it is again ml minus 3 density. Beta is predation factor. So it will be mass upon per unit density. Okay. So this will be rho T inverse. Rho is ml minus 3. Okay. So beta 0 is again initial density. So it has the same dimension. Yes, sir. So step 2, what you will do? We are going to use the scaling here that I have already mentioned you. We now discretely separate the variable into 2 parts. That variable b and small t. How many variables this differential equation has that I have mentioned? There are 2 variables b and t. T is the independent variable, b is the dependent variable. So we are going to separate this b and t by using the two things, right? A new variable, that is your b star and t star. For t star, for b star. And we are going to use a quantity that is for in both the things u and z that will be suitably chosen. Okay, u and z. So the quantity is b star and t star, and the variables that we are going to use, this is u and z. So b star and t star we have to choose, but we have to choose in this way so that u equal to b by b star and z equal to t by t star. Okay, and once after defining these 2 variables u and z, and using the chain rule, dB over dt will be what? You see, b is the function of u, so I can write dB over du, and u will be again the function of z because it is defined like that, du over dz, then dz over dt. So if I put all the values of these derivatives, then it will be, because dB over du will be b star du over dz 1 upon t star, and substitute u equal to b by b star, z equal to t by t star in the equation, differential equation, then the differential equation will be converted into this. Yes, sir. So now you choose the beta star equal to alpha and t star equal to alpha by beta. Then we check the dimension of u and dimension of z, because these are the new variable. You recall, they should be dimensionless. So when I'm checking this is coming out 1 and 1. So they are pure number. So u and z are dimensionless. This is the first thing that we have to check. The new variables should be dimensionless. Thus, both the variables u and z are dimensionless. T star equal to alpha and t star equal to alpha by beta. In the equation, we have this simplified equation. Yes, sir. So after this, what we do, we define the new variables a equal to r alpha by beta, because here you see in the coefficient of u, you have r alpha by beta, and in the coefficient of this u, in the denominator of u, in the bracket, you have the k by alpha. So in this place of k by alpha, you define b. In the place of r alpha by beta, you define a. Then you will have the new parameters a and b in the system, and your your model will be very simplified. Then we have to see that what are the units of these 2 new variables a and b. Then again we check the dimension of these 2 variables, these 2 parameters a and b, and they are again coming 1. So they are again dimensionless parameters. So parameters are dimensionless, new variables are dimensionless, U and Z. So that means our task is done. Yes, sir. So what about the initial condition? You have B0 equal to B at 0 equal to B0. So B was what? You recall B was U times B star. So B0 will be B at 0. So U0 B star. So U0 will be B0 upon B star. But B star you have defined alpha. So B0 by alpha. So this I call this is gamma. So let us check the dimension of this gamma. So dimension of gamma is again 1. So the pure number. So the initial condition is dimensionless now. Yes, sir. So what actually finally we have obtained by non-dimensionalizing this model, we have this model. This is having only 2 parameters A and B, and the initial condition is also dimensionless. So in the initial model, you are having 5 parameters, but here we have only 3 parameters. There, all the variables and parameters were having unit, but this model, in this model, variables and parameters are unitless. So this is a very simplified equation. Now you can study and you can play with this equation. You can choose any value of A and B by taking care of the combination of parameters in which A and B are defined and their physical meaning, and then you can investigate the dynamics of this model system. Yes, sir. Now, what are the advantages? As I told you that if you are going to non-dimensionalize any system, then what are the advantages of that? So how it is beneficial? First thing is that you have seen in the previous example that from 5 parameters, you are left with only 3 parameters. So it makes the simple, the given system very, very simpler. So once the variables and the parameters are unit free, then you can do the analysis of the system without taking care of units and dimension of the given variables and parameters. Once the result of this new system are obtained, then everything is recoverable. Then you can go and see the combination of parameters, and you can predict the situation or the scenario for your original system. So after the analysis, we finally have the result for the original system, where result of non-dimensionalized or simpler model system. Yes, sir. And also, once you have the complex system or higher order system, then it may have the many number of variables when you are going to convert it into the system of first order differential equation. So in the complex system, you may have the many number of parameters. Those systems, actually, this non-dimensionalization is a very good technique. And very precisely, if you want to understand, suppose you want to find out the equilibrium points for the given biological system, because this is one technique that gives you the many information about the dynamics of the system, about the trajectory, how they are evolving in the model system. So once you find the equilibrium points of the new system, non-dimensionalized system, this is easier system, you can easily find out. Then by the one-to-one correspondence, the relation between the parameters and variables, you can go and you can talk about the equilibrium points of the original system and its stability. So what actually is there? There is a one-to-one correspondence between the original system and the non-dimensionalized system. Yes, sir. So this one-to-one correspondence help you to check about the stability and the equilibrium points of your original system. I will make you understand this, what I am telling you, by taking a very simple example of logistic model. You all may be very well familiar with this. dn over dt, and t is the density of the species at the time t, and t is the time. So this is given by this equation. So let us non-dimensionalize this. Non-dimensionalized technique is same. You are going to rescale these two variables, n and t, with the help of these two constants, lambda and mu. So n equal to lambda times x is the new variable, t equal to mu times t dash. So lambda and mu are actually scaling parameters, okay? If we substitute n equal to lambda x and t equal to mu t dash and use the chain rule as I suggested you, then this differential equation, logistic equation, will be converted into like this. So now I will make this differential equation. Now you see how many parameters are here? R, mu, k, lambda. 4 parameters are here. So I will make this differential equation parameter free. So we choose mu equal to 1 by r. So as the coefficient of x, there will be no parameter. We choose lambda equal to k as the coefficient of x in the bracket. There will be no parameter. So this will be dimensionless version of the logistic equation. So dx dt dash will be x into 1 minus x. Now it has no dimension. And also without loss of generality, you can replace this t dash by t. You can write in the same pattern as you have chosen here. this differential equation will be dx over dt equal to x into 1 minus x. Yes, sir. Please go ahead. So you see, this differential equation has no parameter, and you can easily find the equilibrium points. What are the equilibrium points of this dimensionless differential equation? Logistic system, x equal to 0 and x equal to 1. Just put the right hand side equal to 0. You can calculate it. So by the 1-to-1 correspondence, and also you can check x equal to 1 is stable and x equal to 0 is unstable. So, but you have defined that n equal to lambda x. So whenever x equal to 1, I replace x by 1. So n equal to lambda, but lambda is defined lambda equal to k. So n equal to k will be the equilibrium point of your original logistic equation. Because x equal to 1 of the non-dimensionalized system is stable, so n equal to k of the original system will be stable. So this is how you are getting advantage of this non-dimensionalization by the 1-to-1 correspondence of the stability of the equilibrium points and calculating the equilibrium point. Similarly, x equal to 0 is unstable for the non-dimensionalized system. If I put x equal to 0, the n equal to will be 0. So n equal to 0 is again the equilibrium point of the original system, and this is unstable. So in this way, you are just taking the help of the non-dimensionalized system. Yes, sir. So now, on what thing actually this non-dimensionalization depends? This depends on the goal of the study. What actually you want from your model system? What kind of dynamics you want to check? So suppose you have the logistic model with this harvesting, constant harvesting. So this model is given by this. And if we non-dimensionalize in the same way as I have done for the logistic model, then immediately you will have dx over dt equal to this. Okay. And by setting all the parameters, you will be left with dx over dt equal to 1 minus x minus gamma. Why actually I have non-dimensionalized like this? I am having here a parameter in the place of constant harvesting h. The reason is that I want to check the impact of harvesting on the population survival. What impact actually it will raise or it will leave on the survival of the population. So I am non-dimensionalizing like this. If somebody may not be interested in gamma, then they might be interested in the intrinsic growth rate, the impact of the intrinsic growth rate on the population dynamics. Then they can non-dimensionalize like this. You see here in the last differential equation, dx over dt equal to phi x 1 minus x minus 1. So by seeing all these calculations for the non-dimensionalization, one is very clear that non-dimensionalization scheme is not unique for any given model. There may be many schemes for the non-dimensionalization, and it depends on the goal of the study. What kind of analysis you want to do? Yes, sir. So this is like that. For this simple model, actually, you can have the many non-dimensional scheme. And also there are two kind of people, the two class of people. The biologists, what actually they are interested in the experiment and the exact units of the parameters, and they are interested into the prediction of the system behavior. They want the same parameters and their units, so they are not interested in the non-dimensionalization. But there are class of people who are mathematicians. They want to simplify the system, make the system very easier, and so that they can analyze the system easily. So this is the reason actually I have told you that depending on the goal of study, you will have the different kind of non-dimensionalization scheme for a given model system. Yes, sir. So, for example, for the logistic equation with harvesting, you may be interested to see the impact of the carrying capacity. Somebody may be interested to observe the intrinsic growth rate, effect of the intrinsic growth rate. Somebody may be interested to observe the harvesting rate impact on the survival of the population. So accordingly, we have to non-dimensionalize the system. Yes, sir. So you see, for this system, we have three types of non-dimensionalized model. One is this, second is this, third is this. So in the first one, we are interested in the impact of the harvesting on the population. In the second one, we are interested into the impact of the intrinsic growth rate. In the third one, we are interested into the carrying capacity, impact of the carrying capacity. So accordingly, we have three types of non-dimensionalized scheme. Yes, sir. I hope that you people have understood up to this. So this was the second part of the non-dimensionalization. Now, to make the things very clear and rigorously to learn how to non-dimensionalize any given model, we are going to take a bacterial growth model. And by the non-dimensionalization of this model, we will try to learn how the parameters are converted into the new parameters. New parameters are the dimensionless, how you get the new variables. And in process, you will also learn the many things related to the modeling of this kind of system. So I'm not going to start the modeling of this bacterial growth with the very initial level, but here I'm mentioning some assumptions. Those will help you how we are getting the idea. In bacterial growth, one assumption may be very appropriate that if the system of bacterial growth run out of food, suppose there is no food, then the bacteria will start dying. For survival of bacteria, food is required. This is one assumption. So whenever you are going to model it exponential function, right, then in that case, actually this assumption will fail there. So we have to take the assumption of the food also, right, availability of the food also into the model system. So here we assume a situation that we always supply food to bacteria. So we have to supply the food to the bacteria so that they can survive. So only for the growth, we don't need the food. For their survival, we also need the food. So if you maintain the continuous supply of food in the system that is created, it is called the chemostat system. So chemostat is a tank that got bunch of bacteria happily growing into it, and we are putting food all the times. We are taking food out of the tank, just making new food into the tank. So this is the very simple and crude definition of chemostat. Yes, sir. So suppose here NT is one variable and is the function of time t, and its unit will be the volume, number of bacteria per unit volume. Ct is the concentration of food, its unit will be weight, right? Weight of the food per unit volume. So there are two different units of bacteria. Generally we use one unit we use number of bacteria, other one we use the concentration of bacteria. So here actually we are going to use the concentration of bacteria, number of bacteria per unit volume in this model, okay? So could we have the different amount of food at the first in and the second? You see, there is a tank, you are supplying food and food is getting out. So the question is this, could we have different amount of food at first in and the second in? Yes, sir, next slide. So this is the question that we want to answer. If you answer this question, so this I have shown, maybe visible to you, not much, but this is the tank and the flow is coming in, flow is getting out. N and C, bacteria and food concentration is there. So flow in and flow out. Yes, sir. Next slide. So the question that I raised that whether the amount of food on the two end will be same or not. So could we have in the different way I can put this question, could we have the different amount of food at the first end or the second end? What happens if flow going inside is larger than flow going outside? So if flow in is greater than flow out, then what will happen? The tank will be full after some time. Okay. Similarly, if flow out is greater than flow in, then at some point the tank will be depleted. So both the scenario we don't want. Hence, we maintain the flow. Flow in is equal to the flow out. That's it. This is the main idea. The flow of the food is set up here because bacteria needs some kind of food always to survive. Yes, sir. This is the main idea of this model, this chemostat. We first develop the equation for the growth of bacteria, then we will go developing the equation for the rate of change of food. Okay, so if you want to develop the growth equation for the bacteria, then let us ask some question. Are bacteria coming into the tank? You are supplying the food, so there is no bacteria coming into the tank. Only you are supplying the food. Bacteria is going into the tank. And the second question, are bacteria from the tank? Yes, surely they will go. They are not going to stick into the bottom of the tank. Otherwise, survival will be an issue. So they are well mixed. We are assuming this, and they are going partially out from this tank. Okay, as the food is going out. Yes, sir. So we assume that bacteria and food are well mixed in the system because if you assume, because there are some assumptions, people think that okay, bacteria will stick into the wall, but we are not assuming this. If they are not going to for better survival. If they are sticking to the wall, then survival will be one issue because their friends may be surviving well into the tank. You want actually scrap the tank wall so that they do not stick there. And in this way, we are assuming that there is better mixing, proper mixing into the tank. So due to this, there is no bacteria stepping on the wall, and all the bacteria proportionally are going to leave the tank with the flow. With the flow, they are proportionally going to leave the tank. So if there is no food we are assuming, then the bacterial growth you can consider like this, dNOdt equal to Kcn. This thing you have to learn how we have written. This is just simply idea is the exponential model idea. Okay, so Kcn. So we are assuming that the rate is the function of food concentration here. So dNOdt equal to Kc into n. So how you will put the idea of bacteria going out from the tank into this, then you will have the bacterial growth model for that. Okay, so only I have to write here the flow getting out, how many bacteria will get out in unit second. Yes, sir, unit time. So suppose so a crude idea maybe you just subtract minus n, but this will not be correct. Actually, this bacteria is going out with the flow that you call flux. So here it will be proportional to F. So here you should have the minus Fn in the place of n. Okay, so the growth rate equation for the bacteria will be dNOdt equal to Kcn minus Fn. Whether it is going to work or not, we will see it later on. Okay, in the dimensional analysis. Yes, sir. And similarly, if you see the rate of concentration of bacteria, then it is modeled like DCO dt equal to minus alpha Kcn. How much concentration will be getting lower, that much bacteria will be growing. And so the concentration, the equation is written like this. So you see, you are providing the food into the tank and food is getting out. So whatever food is getting out, this will be modeled by minus Fn. And if you take the initial concentration of the food that is getting in C naught, then it will be modeled by plus FC naught. So the whole equation of the food concentration, rate of change of food concentration will be DCO dt equal to minus alpha Kcn minus FC plus FC naught. And that already for the bacteria we have developed. So this is your model system. Now we'll modify this. Yes, sir. So now our first task is whether my model is dimensionally correct or not, whether the dimension of both sides are same or not. So for that, you just separately find out unit of each term and then put there into the equation. Unit of n is what? Number of bacteria per unit volume. Unit of F is what? Volume over time. Unit of K is 1 upon time. Unit of dN over dt, this derivative rate of change of n. So number of bacteria upon volume into time. So for the consistency of the first equation, we need unit of left-hand side, that is dN over dt, is equal to the unit of right-hand side, Kcn minus Fn. So these two units should be same. Yes, sir. Okay. So let's talk about the unit of left-hand side. So unit, if you talk about the left-hand side, this is number of bacteria upon volume into time. Unit of right-hand side, if you will talk, you see 1 upon time into number of bacteria upon volume minus volume upon time into number upon volume. So in the right-hand side, you will be left with number upon volume into time minus number upon time. So if you want to make the equation, the first equation dimensionally correct, so you see left-hand side, you have this. In the right-hand side, first term has this, but the second term does not have this. So if I divide the second term by volume V, then immediately its dimension, the dimension of all the term, first and the right-hand side, two terms will be same. So that means this F should be divided by V. This is giving us message. So the first equation will be dN over dt equal to Kcn minus F by Vn. And similarly, you do in the second equation and you will learn that a second equation is also dimensionally correct. Okay. And there is logic behind that. You cannot talk about the flow without the volume of the tank. If the volume of the tank is full, then the flow will be different. So they should come together. Okay. Yes, sir. So second equation, we need not to check. It is dimensionally homogeneous. Now let us talk about this Kc. How you can set up this Kc. If I take Kc equal to A into C, A is some constant, it will not be appropriate. That means you are saying that if we provide high concentration of food, you go to the first equation, Kcn. Kc is Acn. dN over dt will be higher and higher. That means if you are providing the arbitrary amount of food, then the arbitrary bacteria will divide arbitrarily. But it will not happen actually. At some point in time, bacteria need some time to grow. So that means we have to use for Kc some saturated function. So what is the simplest saturation function that you use as the function of x upon 1 plus x? So in the terms of K of C, what will be the saturation function? This will be actually C upon 1 plus C. Yes, sir. Okay, because Kc is there. So I have just plotted here. It may not be visible. I think you people will be familiar with the saturation function. Yes, sir. Go ahead. So you see how you are going to set up this Kc equal to K max upon Kn plus C into C. So you see amount of this Kc will saturate. It will saturate at the level, right? K maximum saturation level of Kc. So Kc will saturate at the maximum saturation level. So I am in the numerator, I am putting K max. Because when you have C upon 1 plus C, then it will saturate at 1. But when you have the coefficient of C, something K max, then it will saturate at K max. So this is the maximum saturation level. And when you are having here 1, then the saturation constant was C equal to 1 was at C equal to 1, the saturation level was half. So it was calling, we are calling C equal to 1 as the half saturation constant. But when you have in the place of 1 Kn, then Kn becomes the half saturation. Kn Kmax2. That means at C equal to Kn, half saturation is obtained. So what this Kn tells you? This tells you that how faster the rate is, right? How faster the Kc is saturating. And this Kmax gives you the maximum saturation level. So with this idea, if we modify our model, then our model will be this. Okay, yes, sir. Correct. So with this model, we are going to talk about the dimensional, this is dimensional homogeneous or not. So how many parameters this model has? This model has 6 parameters. So we are going to now have the new model, okay, by the scaling system. So what we do, as I told you already, that non-dimensionalization is a change of variable technique that has very nice properties. This is going to reduce the number of parameters. This is going to make everything in the equation unitless. So we are going to introduce some new variable. In the terms of new variable, we are going to have the new model system. Yes, sir. Now you see how you introduce the new variable. You are going to rescale each of these variables by a constant. So generally, actually, we use the constant for the rescaling. The variables nct, we use the new variable n star, c star, and tau. So n equal to n star n cap, c equal to c star c cap, and t equal to t star tau. So if I use this combination of parameter and variable, I put here, so n cap tau will be outside in the both the equation. In the right hand side, I replace the n by n star n cap, c by c star c cap, and t by t star tau. Yes, sir. Next slide. So after putting all these and cancelling the terms, we will reach to this equation, right? And also we multiply the both side by tau, then we have left with this equation. Yes, sir. So now these are the combination of parameters. Those actually has to be adjusted by choosing the value of n cap, c cap, and tau. These are 3 new parameters with the help of which you have scaled your system. N, c, and t. Old variable are what? N, C, and T. New and the parameters with which you have rescaled those N, C, and T are n cap, c cap, tau. We have to choose n cap, c cap, tau so that the number of parameters are reduced. So let us talk one by one. One term is Kn by C. So to make this Kn by C equal to 1, Kn by C cap, how you will choose the C cap? C cap, I will take the Kn. So Kn upon Kn will be 1. So hence this term will be finished totally. So I choose the C cap equal to Kn. For this f by v tau, we have to choose the tau. Tau is the new parameter with which we have to scale. Tau equal to v by f. So f by v into v by f, it will be 1. And the biggest term is alpha k max n cap tau upon c cap. So biggest term is this. So here I have to choose n cap. So for n cap, I take, it's just reciprocal, okay? C cap upon alpha k max tau. And we have already the C cap and tau. Tau equal to V over F, C cap Kn. So if I put the value of C cap and tau, then N cap will be Knf upon alpha K max V. So all these N cap, C cap, tau, if I put into the previous equation in the previous slide, yes, sir. So actually we are going to get this model, dn star over dt star equal to this, dc star dt star equal to this. And to make it more precise, we will define 2 new parameter, k max v over f will be in a parameter alpha 1, and then c naught kn will be a parameter alpha 2. And I put these 2 parameters into the previous equation here. Then we have these 2 equations, dn star dt star equal to this and dc star dt star equal to this. So how many parameters this system has? Only 2 parameters. And the previous one, how many parameters it was having? 6 parameters. So see how simpler system you have got. This has only 2 parameters. But by seeing the impact of alpha 1, alpha 2 on the growth of or survival of N star C star, you can again go back to analyze the impact of your older parameter, whatever you have, Kmax and everything, then you can judge the impact of those parameters for the original system. Yes, sir. Okay, so this is your system, new system, and it is much simpler. As I told you, alpha 1, alpha 2, you are unitless. We can check. Let us check whether alpha 1 is unitless or not. Alpha 1 is what? Alpha 1 is K max V over F. So what is the dimension of K max? 1 upon time, unit. 1 upon time into dimension of V, volume, and dimension of F is flow, volume upon time. So volume, you see, time upon time will be go up, and volume, so it will be unitless. So we are checking that alpha 1 is unitless, similarly alpha 2 is unitless, and we have defined in such a way that N and C are unitless. Sorry, N star, C star are unitless. But without loss of generality, we just replace N star by N, T star by T, C star by C, and you are left with this system. Yes, sir. So here I have just given you 3 references. The first reference is the reference, the basic things you can find in this book that I have talked about today. In the second reference, the model that I have taken, the very first model in this paper in the Journal of Animal Ecology. This is journal from the British Ecological Society. You can take from here. And the other model that I have taken that you can obtain from this MCOT paper and are similar, this book by the MCOT are similar books, right? Or some paper you can obtain from there. Yes, sir. So this is all from my side. And if you have any question, you are welcome.
So thank you so much, sir, for
Thank you.
very
Thank you.
clearly and beautifully explaining this concept of non-dimensionalization, and through the bacterial growth model, you have actually very well illustrated the application of this concept. Actually, I was wondering what is this non-dimensionalization and then what it is, but you have beautifully explained it. So now I leave the stage for the audience. If you have any questions for Dr. Tripathi on any of the concepts he has discussed.
Darshan sir, I think there are lots of questions in the chats. Maybe let sir answer first, then we'll open to audience. In the
Okay.
chats, there are lots of
Yeah,
questions.
I'm seeing it. Yes, I'm seeing that, sir. So in the starting, we have this, can we non-dimensionalize the non-linear differential equation with non-monotonic saturation incidence and delayed treatment? Yes, we can do this. The delayed system are also non-dimensionalized, okay? We have been doing this, you can check it. So you have to be careful about the delay term, but it could be non-dimensionalized, okay? We are taking a new model, finding dimensions to dimensionless, then finding equilibrium points and stability. After that, we are finding bifurcation also, how to use in real life. Okay. So for using in real life, actually, suppose this is what I am talking about. Now, this is theoretical kind of things, but now experimentation is required for this. Experimentalist, biologists or ecologists, they are much near than us for the real application of the result that we are giving here. But whatever the study we are presenting here, those are theoretical study, but the theoretical study by this kind of calculations, by non-dimensionalization, then coming back to the original system, giving the idea about the original system, these kind of results are going to help the experimental biologist or ecologist. Then they can take the idea from there and they can work out accordingly. So it is like a cyclic process. It's not like that somebody is going experiment. The theory will suggest what kind of experiment they have to do. Then, and the experiment is much more near to the real application. Okay. But you are not going to actually distract the any disturbance to the system. You are just taking the linear kind of scaling and you are coming back to the new system, and with the new system you are coming back to the old system to talk about, so that easily you can use the mathematics to analyze the system.
Sir, I'm tempted to add, sir, to this question.
Yes, sir.
Can I add a bit, sir? So, as sir was telling, yes, of course, it is applicable to theoretical bio or sir, experimental biologists. But when you come to epidemic model, who sir has asked that question, so we can find especially what is called as a disease-free equilibrium and infection-induced equilibrium. So, if you want to make the system to go to a disease-free where the infection is not much, so how should you reduce the reproduction number to be less than 1? So it can actually, in the model, we can incorporate the strategies. And in fact, we can drive that if you implement these strategies to this extent, in fact, we can show that you will reach a disease-free equilibrium. So these are all like, there are many real-world examples in what I'm saying is in this dynamical systems when we model and do. And also, sir, as you actually know that when we add optimal control theory, we take it more
Yeah,
applicable to reach to
correct,
the
correct, sir.
level, sir, that level. Just thought to add, sir. Sorry
Correct,
for
correct.
interrupting. Please go
Yeah,
ahead, sir.
very, very good, sir. You explained well. Actually, this
Yes,
is
yes,
more realization, like how we are talking about the real things.
yes,
Yeah,
yes.
there is
Please
one
go ahead,
more
sir.
question. What are the textbooks for the nonlinear dynamics basics for new learners? Okay, so one book is by Stephen Stugotz. If you are basic learner, then you can see this book by Stephen Stugotz. Uh, the title I did not call. So you just put the Stephen Stugotz. There is one very popular book. It has more than 25,000 and he is living legend of the nonlinear dynamics. So you can read that book. Firstly, you will get interested into the subject. Then after that, if you want to learn the mathematical things more rigorously, then go to the some books from the area of dynamical systems. Like you can see the book of Hirsch by the Hirsch, Ismail and Danway. Then again, one book is there by the Lawrence Perko. You can see all these books. Yes, sir.
Yeah, thank you, sir. Anyone else has any other comment or question you can ask? I think there are no questions. So we thank
Yes, sir.
Dr. Tripathi on the behalf of the center and also on behalf of Sri Sathya Sai Institute of Higher Learning. We uh, we are grateful to you for sparing your time and sharing your valuable knowledge. We also look forward to for the future talks and other
Sure, sir.
interactions.
So
Thank you so much.
I am also
Thank
very,
you,
very
sir.
much thankful to your Center for Excellence in Mathematical Biology and your institute. You people have given me opportunity to talk on this platform. I am very much happy and we shall be connected in future. Okay, thank you very
Sir,
much, sir.